Hi, Mitch Winger back with another video on data analytics and machine learning. In this video, we'll discuss ways to avoid overfitting. Hope you enjoy. Okay, let's get started. More complexity in our data mining model causes it to include more and more spurious correlations. We can make a model complex by adding more attributes to our linear function, or by adding more branches and nodes to our decision tree. What this does is it allows the model to include more and more peculiarities of the training data in the model, even when they don't represent what occurs in the wider population. If we evaluate our model on the same data we trained it on, it's not that useful in assessing how well the model will generalize to unseen cases in the wider population. What we can do is create a sort of lab test of generalization performance. We hold out some data from the training data set. Remember, the target attribute is already labeled for this data. We won't use this holdout data to build our model. We can now estimate the generalization performance by applying our new model to the holdout data and see how the predicted target values compare with the labeled values. We often refer to the portion of the dataset that we use to build the model, the training set, and the portion of the dataset that we hold out, the test set. What we find is that the model continues to gain accuracy with complexity for the training set, but accuracy only improves to a certain point with the test set, and then it starts to decrease. We can actually chart that performance on something called a fitting graph. We can build a fitting graph based on the error rate we find in our testing. You can also create a fitting graph based on the accuracy rate instead. As we expect, our predictions become more and more accurate as we increase the complexity of our model, at least for the training data. Let's see what happens with the holdout data. Prediction accuracy improves here too, up to a certain level of complexity. After that, the error rate begins to increase, and the performance of our model on the holdout data gets worse and worse. Now, not all fitting curves will look the same. Each curve is going to be unique to your data and to your model. So we'll get back to fitting curves in a bit. What should our model be able to outperform? Well, if we consider a classification dataset with two classes, and the dataset is split evenly between the two classes, I should be able to achieve, on average, 50% accuracy just by selecting the positive class every time. What about a distribution of 60-40? Well, in that case, I should be able to achieve 60% accuracy by just selecting the majority class every time. Or in other words, my error rate should average about 40% there. Now, in both these cases, the 50% or the 60% accuracy or 40% error rate would be considered our base rate. Any model we consider should outperform the base rate. Now, note that overfitting can occur with both linear and tree-based modeling approaches. In a decision tree, if we let the tree build out until each decision mode is completely pure, i.e., we have no entropy left, we've more or less built the equivalent of a lookup table. The tree will be a little bit better than a lookup table because it will most likely be able to create some type of estimate for new unseen examples where a pure lookup table wouldn't be able to do that. Now here's another fitting graph, this time with accuracy on the y-axis. Remember, we saw error rate on the previous one. So the fitting graph looks a little bit different here, but the concept is exactly the same. Here, we're evaluating the size, number of nodes of our decision tree versus the performance. And what do we see? Well, if we have just a very few nodes, well, then we have poor performance for both our training and our holdout data. And as we add more and more nodes, we see that we get better performance on the training and the holdout data up to a certain point. And then once we reach that point, then we start to have too many nodes. Training performance continues to improve up toward full 100% accuracy, but performance on our holdout data begins to get worse and continues getting worse the more nodes we add. So, what is our sweet spot? And in this case, it appears to be somewhere around 100 nodes, give or take. Let's walk through an example of how this can happen. Let's say I have a data set of 16 observations with a categorical attribute related to age and whether the individual bought our product or not. I split my data set into 8 training observations and 8 holdout observations. If I split on age greater than 60, I achieve an 87.5 accuracy rate with my training data. I'm correct with 7 of my 8 predictions. Now, how does our model perform on our holdout data? Well, as it turns out, our model also predicts 87.5% of the target values correctly in our holdout data set. Not bad. Now, let's try adding a new feature to our data set. And we're going to make this feature a random feature, which will assign a 1 or a 0 randomly to this new attribute. Let's see what happens. So we've added now our new random attribute, and that allows us to add more complexity to our tree. The subgroup age greater than 60 is already pure, so we don't need to partition any more there. But I see that I can partition my other subgroup by my random feature and achieve 100% accuracy with my training data. Now we're cooking, right? However, if I apply my updated tree model to the holdout data, performance doesn't go up. As a matter of fact, it goes down to 62.5%. This is because our new random feature was completely unrelated to anything else in our data set. But the chance distribution in our training set made it seem as if it was a useful bit of information. Fortunately, by testing our new model against some holdout data, we can get a feel for how our model will perform out in the real world. Unfortunately, there is no good automated way to determine whether a model has overfit up front. We can estimate what our population will look like and use that to help balance model performance against overfitting, like we've seen in these examples. Using holdout data, however, certainly helps. Now, holdout data is useful, but it just gives us one estimate of how our model will perform. Should we bet the company on one test? How representative was that split we got in our data when we selected our training and testing sets? What's more, holding out data leaves information on the table that we could have used to provide the model with additional training. This can be especially critical if we don't have a large amount of training data to begin with. Instead of a simple holdout, we can use an approach called cross-validation. Cross-validation uses a training holdout approach, but it uses a systematic approach that builds multiple models and tests each model using different subsets of the data. It works by partitioning the data into K partitions, which we call folds. We then run K tests of model building and testing. Each time we hold out a different fold for testing and use the other folds for training. Cross-validation has some similarities to the bootstrapping approach you may have used in statistics in the past. Cross-validation has a number of advantages over a simple holdout approach. First and foremost, it makes better use of your data. All your data ends up being used both in model building and in testing. Each example will be used once for testing and then multiple times for training. By providing multiple estimates of your model's performance, you can calculate mean performance and performance variance for your model, which can be extremely useful in helping assess the usefulness of your model and the level of confidence you can place in it. Let's say we decide to use cross-validation to assess a classification tree and logistic regression for our churn example. If we create 10 folds in our cross-validation testing, we may find that the mean accuracy of our classification tree is slightly better than the mean accuracy for our logistic regression. Let's say 70% versus 68%. So far, we might be fine using either approach. But if our logistic regression has a much higher variance across our testing folds than our decision tree does, we will then greatly favor the decision tree, as we expect it to provide much more predictable, consistent performance across different data sets. So, getting back to our problem of overfitting, we've got a number of techniques we can use to address it. We can simplify our model. We can use fewer features in the model. We can limit the size of our decision tree. We can use simpler, less flexible models even. Pruning is a technique we can use in trees that we'll discuss. We can also enrich the data a couple different ways. We can enrich it with influential predictors. We can enrich the training data with more observations. We can get more data. We always want to check the compatibility of our training and our validation data sets as well. Now, these remedies may or may not work, just depending on what the source of the problem is. In general, we find that if we have a small number of observations, that does tend to favor regression, while if we have more observations, that favors classification trees. Obviously, the more parameters you have in your data set, the more likely you are to find overfitting at some point in your model building and find that you will have to deal with it. That's it for our discussion on avoiding overfitting. Thanks for watching. As always, be sure to check out the other videos in this series.